Hello and welcome back to our final section. We are almost done with Chapter 2. Today we're going to be looking at absolute value equations and inequalities. Now in Chapter 1 we did go through absolute values and what they mean with numbers, and we're going to combine that with what we've learned with linear equations and inequalities and combine them. So first, we're going to review over the little distance definition that we had. So, we already know that if the absolute value of x equals 4, then that means x has two possibilities. Either x is 4 or x is negative 4. If you plug in either one of these numbers, you'll find that the absolute value of them is 4, because that is how far they are from 0. Now we use this distance formula to look at the next case. X, the absolute value of x greater than 4. This, in fact, is every x that is either greater than 4 or less than negative 4. You could say, the best way to put this is every value of x that is at least 4 away from the origin. In which case, every number greater than 4 is, obviously more than 4 away, and every number less than negative 4 is also at least 4 away from the origin. Now, what if we turn this around and go absolute value of x is less than 4? So now we want all x's that are less than 4 and greater than negative 4. And if you think about this, especially if you look at this first and then this is our little tri-inequality. So it is actually just all x's that are between negative 4 and 4. And in distance terms, this is all x's that are within 4 units or less from the origin. So if 1, negative 3, negative 1.5, all those numbers are within 4 from the origin. Now we want to start solving these absolute value equations and inequalities. So, well, the first case is the absolute value of ax plus b equals k. This, just like our initial distance case, has only two solutions. Either it equals k or it's going to equal the negative. Either way, because obviously the absolute value of k is k, absolute value of negative k is k. So if you have absolute value of ax plus b equals k, you just split them up into two equations and solve each one independently. Case 2, we're looking at all numbers that are greater than k. In this, you split it up very similarly. You look at ax plus b greater than k as if you just took the absolute values out. And then, it's very similar to the properties when you multiply by negative, you flip the sign. You do the same thing here. So, because we're looking at the negative part of it, we want to flip the sign. So we go from a greater to a less than. And then we know that the answer is this or this. So this is a union problem. And you just solve each one independently. And then you just have the union of both cases. The final case, of course, is when it's less than k. This is just like the third distance example that we had the previous slide. We want everything that is between negative k and k. So we set this up as simply a tri-inequality and then just solve from there. So now, for our first example, we're going to do the simple absolute value of 2x plus 1 equals 7. So first one we'll do is the simple one. Just plain old 2x plus 1 is 7. So we just move the 1 over, divide by 2, and we get x equals 3. And of course, plugging that in, we would get 6 plus 1, which is 7. And the absolute value of 7 is 7. So this is one of our solutions. Now we need to consider what if it equals -7. Well, again, we move the 1 over, divide by 2, and now we get x equals -4. Now, it does seem weird, but if we plug it back in, we go -4 times 2, we get a -8, and we add 1, we get -7, which absolute value of -7 is 7. So x equals 3 or -4. Now let's look at the same thing, only this time we're going to go with greater than 7. Well, we still set it up the exact same way, only instead of an equal sign, we still keep the greater than. And it just follows almost exactly the same way. In fact, if you look at the previous slide, the only thing that changed is these are no longer equal signs, these are greater than signs. So now we have x is greater than 3. So any number larger than 3 will satisfy this equation. But now we need to look at what if we picked a number that was smaller than -7. Well, in that case, again, just like the previous slide, we're doing the same thing, except instead of an equals, it's a less than. And again, we flip it from this because we're dealing with the negative number. So again, we solve through it, and we get x is less than -4. So any number greater than 3 or less than -4 will be an answer to this equation. So now we get to our third step. Suppose we want absolute value less than 7. As we said, this is our third case. This is our tri-inequality. We want all answers that are between -7 and 7. So just like our other tri-inequalities, we will first subtract 1 from all 3 to get -8 less than 2x less than 6, and then divide through by 2, and we get x is between -4 and 3. What's so great about these, especially ones like these, if you'll notice, the 3 and -4, they showed up in all 3 examples. What changed was how they related to x. The first example, it was either equal to one of these, then it was all numbers less than, all numbers greater than, and then in this example, it's all numbers in between. So of course, if we were to consider all 3 cases at once, you get the entire number line. Now we're going to take things and make it a little bit more complicated. Suppose we have one absolute value and we set it equal to another absolute value. Well, how do we solve for that? Well, as it turns out, because, one could be positive, the other could be negative, or they could both be positive, they could both be negative. Your initial reaction may be that there are 4 possibilities. Well, in actuality, there are only 2. We only have to consider when the absolute values are just gone, so they're both positive, or we consider where one is, say, positive and the other is the opposite of what's inside. And the reason for this is, if we were to consider the negative of the inside equal to the negative in here, well, that -1s would just cancel out. So that would actually give you the exact same answer as this one. And on this case, suppose we went with the negative of this one and the positive of this. We would actually get the same answer because all we did was we multiplied both sides by -1. We just moved this negative from here to over here. So you think there are 4 answers when in fact there really are only 2 answers. So let's go ahead and try this out. We're going to start with absolute value of x plus 6 equals absolute value of 2x minus 3. So first let's consider they're both the same. We just take out the absolute values and we just solve. So we move the 6 to the right, and we're going to move the 2x to the left. We get negative x equals negative 9, or x equals 9. So if we plug 9 in here, we get 15 here. 18 minus 3, 15 there. So yes, that is a solution. Now we need to look at the opposite. We need to look at negative 2x minus 3. So from here, we just simply distribute it out, and then we just solve just like we do all other equations. We're going to move the 6 over to the right. We're going to move the negative 2x to the left, and we get 3x equals negative 3, or x equals negative 1. So if you plug this back in here, you get negative 1 plus 6. That's 5. If you plug it in here, you get a negative 2 minus 3. Well, that's negative 5. Oh, but it's absolute value, so that's 5 also. So our final solution is either x is equal to 9 or x equals negative 1. Now we're going to look at two special cases of absolute values. And it's just more of a almost like a definition. It's kind of it seems obvious, but it has to be stated anyways. For any real number a, in other words, if we take any number, does not matter what it is, the absolute value is always greater than or equal to 0. Well, that just seems like the definition, because we always knew positive numbers, absolute values, they're positive. If it's a negative number, you just take the negative off, and you got the positive value. So that means, what this means is if you ever came across a case like this where you have the absolute value of something is greater than or equal to, say, negative 4, well, this is always greater than 0. So of course, no matter what this is, it's going to be greater than or equal to negative 4. So any number at all will work in this solution. Also, if say you took the case of absolute value of 3x plus 5 less than negative 2, well, that is just impossible, because we already know absolute value of any number is always positive or 0. So if it couldn't be negative, and it can't be obviously less than a negative. So the only recourse is there is no solution. X is, as I showed before, the empty set. This isn't 0. This is the empty set. Now our second case is another one that seems pretty obvious. This is kind of like a special case of the special case. And that is absolute value of a equals 0 only if a is 0. That means if you have the absolute value of anything and it equals 0, then that can only happen if the stuff inside is 0. So there is really, in other words, there is no point to having these absolute values. If you have this, just get rid of the absolute values. There's no point to them. So in this example, absolute value of 7x minus 3 equals 0. Well, that can only happen if the stuff inside is 0. So we might as well just get rid of it. So now we just have 7x minus 3 equals 0. And we just simply solve from there. We add 3 to both sides, divide by 7, and we get x equals 3/7. And if you plug this back in, you get 7 times 3/7, which is 3. 3 times 3 minus 3 is 0. And the absolute value of 0 is, well, 0. Again, feel free to click on any of these links to kind of review on any of our examples that we just discussed. Make sure if you do have any questions or comments, again, please post in the discussion forums or in the comments on the video right here. Again, so everybody have a good time. I will see you guys in the next class period. We are at the end of this chapter, so be ready. We are going to have a review and an exam on this soon. So take care and be ready.